Okay. Good. So in real difference, in contrast, I should say, with previous presentation, I represent our work done for more than 10 years with great wish to help surgeon to use fiber optic spectroscopy in pragmatic operations. Because what we heard that unfortunately in many operations for resection of tumor, there are problems. Not always margin is very easy to detect, and in result it's a problem, let's say, that sometimes tumor is not removed completely, not radically, and from other side it can be, let's say, maybe too much tissue removed when it's no real big reasons for it. So give me a second. Okay, so in general, biophotonics market is really more and more, let's say, known to the pragmatic doctors as the market where modern technologies, optical technologies, are coming into the everyday use. And I show at this slide that, for example, diagnostics starts to play much more important role than it was, let's say, 20 years ago. If 20 years ago it was really much more treatment and a bit of diagnostics, right now in year 25, treatment itself, it's less than 40%. So it's a lot of actions directed to screening, diagnostics, and also to monitor what's going on after operations. So, and you can see that it's interesting diagram over here that biophotonics in general is today is one of the, how to say, fastest growing segment of the market. Even when these data are from 2018, believe me, today it's information technology and biophotonics are really leading. Why we are focused on fiber optics? I have started a company, Art Photonics, in '98 in Berlin with wish to find promising applications for fibers which can really cover very broad range. So more or less well-known area is from UV to near-infrared, covered by silica fibers. These fibers are used for telecom. It's like more than 1 trillion kilometers for telecom lines in the world. But we are looking for the fibers from another, at another angle. We look how to deliver light through the fiber to get information and to get it not only in that spectral range, visible, UV visible up to 2.5 microns, up to mid-infrared range. And to be honest, my baby is a very unusual fiber. It's named polycrystalline silver halide fiber. It looks like that. Very flexible and really transparent in the range, which is named in, let's say, molecular spectroscopy like fingerprint region. And our fibers, again, so they are transmission spectra. So they are transparent in the range where black body, our body at room temperature, 300 Kelvin, has a maximum emissivity. So it means you all remember corona, when temperature of the body was simply measured in non-contact mode with infrared pyrometer. But problems that with pyrometry, you really can measure only when you have direct access to the subject, which emits infrared emission. You know, this emission comes from here. But our fibers are simply transparent in the range where emission of the black body has a maximum, 10 microns, 12 microns, what else? So that's why in general, there are technology, if we shall complement infrared camera, like this camera, for example, from the company Optron, by fiber optic cable, then we can go inside human body and measure temperature inside human body. Why I mention that? Because in general, any cancer normally is a bit warmer than surrounding tissue. It can be up to half a degree, and sensitivity of fiber optic pyrometry can be 0.1 degrees Celsius. So it means if right now pyrometry is already used to detect breast cancer, because infrared camera can look on the breast and see warmer areas, which is probably the location of tumor. With the fiber optics, it's possible to go inside human body and see tumor on esophagus, on colon wall, in stomach, and so on. So that's why, in general, I see great future for it. But to be honest, we are looking for the partners with whom to develop this kind of infrared endoscopes. And it will really complement the whole market of endoscopes in the world right now, which is about 40 billion today, but all of them are still limited to the range of 2 microns. That's why infrared endoscopy has a great future, and we are looking for the partners, including Singapore. Nevertheless, our work within last 10 years, 11 years was more focused on spectroscopy. And this spectroscopy is realized, for example, with silica fibers, which are limited to 2 microns. It's 1 micron, 2 microns, by so-called first harmonic or second harmonic of molecular vibrations. What you see here, it's acetone absorption bands. So you see how intensive absorption bands, and you can really explain every peak by distinct vibration of the molecule, CH, OH, or what else. And this information is named fingerprint region because in mid-infrared, you see so great spectra when, for example, second harmonic, all the peaks are also present there. But they are about 100 times weaker. They are broader, so it's more difficult to understand what is behind the composition of tissue if you look for that spectra. Mid-infrared will give you very precise knowledge. Now there is alternative technique. This is data relatively old, but they are a bit changed because Raman now is another method to detect molecular vibrations. And that's why with molecular vibrations, again, you can really analyze tissue composition. To help doctors to make less mistakes when they do resection of tumor, because practice today, they used so-called gold standard of biopsy. They took somewhere pieces of tissue, it can be 3, 4, 5 points where they are not sure is it tumor or malignant, but then, it takes time to analyze each spot. And this is not for the whole area of resection, which can be big. So that's why in result, we decided that we should give them a choice of any method, which can be mid-infrared absorption, made with FTIR spectrometers, Raman, fluorescence, and near-infrared. And we created, it was in 2015, we created so-called multispectral fiber system, which includes several spectrometers. So this is infrared, this is Raman, this is fluorescence, and this is mid-infrared, near-infrared. And then we decided that doctor will really use all the methods to compare, to select which one will be the most informative, most precise, because today, quite often situations that spectroscopy is booming, and there are several methods which I already mentioned, and manufacturers of spectrometers, they try to, let's say, sell them and suggest them for biomedical, industrial, pharmaceutical applications. And end users sometimes is lost, which method to use, Raman or infrared or near-infrared. So that's why after the company Art Photonics, which I created and run up to 24, up to the last year, In the last year, I already found a customer company, Nynomic, who acquired Art Photonics, and now we are making complete system. And what you see on this photo, it's several spectrometers on the wheels. It's a trolley on the wheels, which we can move to the surgery room or nearby. Infrared spectrometer, Raman spectrometer, fluorescence spectrometer, and infrared, and all of them with fiber optic probes. So it means you can touch with the end of the fiber, you can touch to the tissue and understand what is the composition of this tissue. Of course, probes must be tiny, flexible, biocompatible, in some cases disposable, because it's a special demands on medical fiber optic probes. We started from experiments in vitro with cancer of kidney, renal cell carcinoma, and then we really moved to the clinics, Charité clinics in Berlin, and we made analysis ex vivo, when it's just a piece of tissue resected, and we have, let's say, 5-10 minutes, to make our analysis. Nevertheless, dream is, of course, to move from ex vivo to in vivo diagnostics, and this is a very good example from our partners in Tel Aviv. This is my very good friend, Professor Abraham Katsir. He is doing analysis of the skin cancer. It can be not only cancer, it can be, of course, a different type of cancer. It's so-called, for example, basal cell carcinoma, BCC, squamous cell carcinoma, SCC, and the most aggressive is, of course, melanoma. For melanoma, and what is done here? It's infrared spectrometer, it's fiber optic probe, and it's very simple probe with a fiber loop. And if you will touch to the surface of the skin, to the different lesions, you will see different spectra. So, for example, in that range, here it's a normal, let's say, tissue, and melanoma has difference. Quite big contrast with a normal tissue. In the other range, for example, for BCC, again, normal tissue looks like that, and it's very different for BCC. Same story with SCC. So it means, in general, it's easy before a patient who does not know what happens on his skin, and he runs to dermatologist. What dermatologists do today, they simply use a lens, okay, with iPhone, with a normal optical lens, and they make kind of preliminary conclusion, maybe it's BCC or maybe melanoma. But to be sure, we should really take a biopsy, so piece of tissue, bring it to laboratory, and in laboratory within 1 to 3 days, to understand, is it really, what kind of tumor or carcinoma is it, So in general, of course, it takes time. It can be not only one lesion, it can be several. It costs money, and it's also, we should not forget that every patient will have a stress when he waits for the results of this analysis. So that's why infrared spectroscopy can be used for the screening applications at any kind of, how to say, sea beach, where the tourists, they see something, but they can get fast diagnostics, really preliminary diagnostics, which will be much more precise than this simple optical analysis under magnification. More deep intervention, and even not a system which was only for the experiments. We are proud to work with the company Reverdi in Rotterdam. That project named Rashua was really also realized with the Erasmus Medical Center in Rotterdam. And in result of this project, the whole system was created, complete system, not only fiber optics. And it's interesting that for oral cancer, of course, margin dimensions must be much smaller, because when we started with kidney or with colon cancer, for colon cancer, sometimes doctors can bring on our table a couple of kilos, and we should detect, where is the margins of tumor. But in case of the tongue or any other tissue inside our mouth, it's very delicate, because if tumor is detected, it must be tongue must be resected, and person could not talk anymore or need some kind of reconstructive surgery. That's why it was extremely important to find where is the border of tumor, where is the margin, to make a minimal invasive but complete resection of tumor. And for that project, we developed one of the smallest fiber optic probe, maybe the thinnest today, which is, let's say, only like a needle. It's a piece of fiber, metal coated fiber with 150 micron outer diameter, with a very sharp nose. And when we push this fiber into the resected tissue, sorry, but we were not allowed, let's say, to make it in vivo. We really did it at ex-vivo, after permission. But then we can really detect where is a piece of tumor and where is a normal tissue. How we distinguish malignant, non-malignant. This is in Raman spectroscopy. It's a special spike of lipids, and this is reflects, concentration of water. So if there is this kind of green ratio of intensities, it's okay. But when it's too much water, then it's tumor, because tumor normally creates a delivery system for water to grow faster. So that's why we can easily distinguish, because this fiber optic needle goes in tissue with a speed of 1 centimeter per second. And every 100 milliseconds, we can distinguish malignant, non-malignant tissue. But not only that kind of application, we really look not only for kidney tumor or colon or, let's say, oral cancer. We developed this system, as I already mentioned, which includes all 4 methods of spectroscopy. And the reason why 4, because one method can already help, but for example, this is fluorescence. But fluorescence can give, this is, for example, tumor, this is tumor, and this is normal tissue. But then it will be too many spots which are so-called false positive or false negative. So that's why when we fuse fluorescence method together with mid-infrared itself alone will also be much better than fluorescence, but same time there are still false negative and false positive spots. But when we made the fusion, it's a mathematical treatment of spectra. This is fluorescence, this is mid-infrared. When we made a mathematical treatment for PSA, so-called, we see that this is really spots related to tumor, and this is all spots from normal tissue. So with much less problems with false negative or false positive spots. So as soon doctor has no time and no maybe even wish to look for spectra of tissue, and no time to make mathematical treatment, we try to develop relatively fast end user software. When in this case it was even 2 probes, when a doctor will see either green light or red light from tumor. It can be even acoustic signal, because this mathematics can be done in real time, and the spectral analysis of tissue can be relatively fast. We tried different combinations. It was, for example, not only like previous slide, mid-infrared absorption and fluorescence. It was also a combination of near-infrared and fluorescence, because it also helps to make more accurate data. It can be also near-infrared and mid-infrared when doctor can distinguish tumor and normal tissue much better if it will be just one method used. And more of it, our latest years, we have developed so-called, it's really innovative, very first combi probes. Combi means we have same probe in hands. This is about 6 millimeter probe and only 0.5 millimeter distal end. We put under this kind of, in this case, cubic zirconia, we put infrared fibers and 2 silica fibers. That's why in one probe, we suck from this spot mid-infrared spectra and fluorescent spectra. This was done not for tumor, but it can be done for tumor. It's simply a lot of work. We try to distinguish three types of tissue for chicken. And you can see that if it will be only one method used, for example, like this one, then it will be fat distinguished, but breast and liver really not distinguished. When we use mid-infrared, it will be better, but still, again, not a complete differentiation of all three tissues. So it was done. We made a data fusion. We really differentiate all type of tissue, but it's unfortunately very expensive equipment. Spectrometers for that range, it's more than 50, maybe up to 70,000. Fluorescence, it's cheaper, but nevertheless, complete system, it's about 100,000 plus big data treatment and so on. While we found, it was our best result, which was published 3 years ago, that we can use one wavelength in mid-infrared and one wavelength in fluorescence and really distinguish all three organs even better than it was done with very expensive equipment. Because this is much cheaper, maybe 20 times cheaper, faster, and it can be also used in food industry, and it can be used, of course, in oncology, or not only for oncology, it can be in other medical applications. I will only mention that we also made a combi probe which unite mid-infrared absorption and Raman spectroscopy. Again, in this case, it was not medical applications, but for example, this is raps oil, and it can be used, for example, for bioliquids, because, for example, trauma for the patient brain or tumor can be analyzed also for bioliquids or for lymph. Again, this is a whole family of different combi probes, and Art Photonics is leading with these new probes. They are already used in pharmaceutical industry, and when the dimensions will be squeezed to medical use, it can be also used, and we are looking for more medical partners to do this. Another bioliquid to show you that milk, one very important kind of bioliquid. You can see that in infrared reflection, all types of milk is very different. It's extremely different when we made a fluorescence analysis. And when we do it with mid-infrared, it's a whole forest of very interesting features. So it means in general analysis with a multispectral system can provide a lot of useful information on molecular composition of tumor before, or maybe not instead today, but it can be even more informative than biopsy. Because biopsy today is just to look something under microscope and see structure of cells. Okay, just to be more close to the end of my presentation, we are not trying to push to the market, let's say, expensive system, which is Fourier spectrometers or even diffraction grating spectrometers. When we develop something, for example, for moisture sensing, we found very interesting an application for prostate cancer. Because here, instead of spectrometer, which costs about 15,000 or 20,000, it was just 4 LED and 1 photodiode. And with this kind of, let's say, simple structure, it was later like a pulp size device. Even with IP address over here, we can easily do the following analysis. Look, it was done ex-vivo again. It was, sorry, it was not prostate, it was kidney. We did, for example, renal cell carcinoma. We made with this simple device, this tiny device, we really made analysis of, let's say, malignant tissue and normal tissue. You see how big difference is it? So it means tiny device. This is less than my half palm. With a fiber optic probe can be really used to distinguish malignant, non-malignant cells, and more of it. Each sensor has IP address, and this IP address allowed to do so-called telemedicine. So if the young doctor will try to use this diagnostics first time, he can ask for the help, I don't know, do an operation in Singapore, asking for the help from Boston or let's say Berlin. Then it will be possible because profi doctor with good experience will see it, because data from this sensor fly to cloud in real time and will be visible other side of the planet in real time. So that's why it can be new era of, let's say, fiber optic spectral sensors to be used for the cancer diagnostics. Okay, this is my couple of last slides. We also do more for medical application. In this case, it was a big European project with 14 partners to detect osteoarthritis in cartilage. And in this case, again, idea was not to use the whole spectra of cartilage to distinguish disease from normal tissue. It was selected 7 wavelengths, and these wavelengths are specific for quantum cascade lasers. Then it was possible to distinguish, because we are able to couple different wavelengths, quantum cascade laser with a fiber and put it in one catheter. And this catheter in this case was going into the knee. So that's why in this case, this device can be used for diagnostics of cartilage, of tumor, in general, because of very narrow intensity for the lasers. It can be used even for the analysis of patient exhalation to detect diseases at early stages. So that's why I made some kind of, let's say, fast review of different fiber optic tools which can be used and will increase a lot capabilities of doctors to make in vivo diagnostics, at least ex vivo, reduce mistakes, which can be from 50 to 70% in detection, in definition of tumor margins. And in result, it will be, let's say, improved, let's say, efficiency of operations. It will be also better life quality for the patient after, how to say, precise resection of the tumor, because chemotherapy or radiotherapy is too dangerous for the body, for immune system, and so on. So that's why we are very open to work with partners, and we have great partners, and knows at National University of Singapore, Professor Zhiwei Huang, who started and was one of the pioneers of Raman spectroscopy for cancer detection. And we are also planning to collaborate much more close with great clinics, and we have also excellent partners at NTU, Nanyang Technical University in Singapore. So that's why we are looking how to create, how to say, partner company in Lux Photonics in Singapore. Unfortunately, I missed my chance to visit Singapore personally for this conference, but I hope that next year I will be at least at APE, Asia Photonics exhibition in February, and maybe we shall really have a very interesting meetings over there. Thank you for your attention, and I show you very briefly that in general, diagnostics market for cancer as well and liquid biopsy is really booming. You can see that it's really growing with a speed of, let's say, 11%, sometimes 17%. My focus was on molecular diagnostics, and here you see that it was the fastest growth predicted for the nearest future. Thank you.